Okay, so hello everyone. Uh, I'm Aniruddha and today we'll be looking at week 4 contents. And hello everyone on YouTube as well. So let us wait for a few minutes till other people join us. Till then, if YouTube audience has some questions, they can ask through the live chat. So perhaps we can begin. Uh, since there are no questions from anyone, let us just start by recalling what we did this week. So the whole week was about extension of given measure. So we were given a measure mu on an algebra A, or in fact, not only an algebra, but any collection of sets of X. So mu from some collection of sets to 0 infinity, we were given a measure, and we were given another collection C prime, which contained C. We wanted to find out, is it possible to get a measure, suppose mu tilde on C prime, such that it is same as mu on C. So, hello Prashantdeep.
Hi, hello, sir.
So, do you want to ask any questions from this week's contents? Yes, tell me.
Yes, sir. Can you repeat?
Yeah, do you have any questions from this week's contents?
Yes, sir. I have a confusion in one problem of assignment number three.
Assignment number 3. Okay. Tell me, what is the confusion?
So I'm sharing the screen.
Okay, share it. Do you want me to stop sharing or something? Yes, it is visible. So, Prasandeep, I think you have to unmute. So, yeah, actually, you're muted. I cannot hear you. You please unmute your mic. Yeah, now it is fine.
So in problem number nine, I have a bit confusion. So how can
Okay.
the sigma algebra and the Borel sigma algebra is equal in this problem?
Okay, how did you come to the conclusion in problem 8?
So in problem number eight, obviously, as you said in earlier, obviously there is the dyadic number are dense, so and I have know that it dyadic number, every real number have a dyadic sequence converging to it from right and left. So
Okay.
sir, okay, then every open interval belong to the this set ID.
No, no. Every open interval does not belong to the ID, but every open interval belongs to the sigma algebra generated by ID, right?
Yes, sir. Yes, sir. So I have that the sigma algebra generated by this ID contains every open interval in my way.
Correct. Correct.
Yes. So it contains the set sigma algebra generated by every open set in real number R. So that how it equal to the sigma Borel algebra. But in
Correct.
ninth, sir, it am I correct?
Yes, yes, you are correct. But in ninth, what is the problem then?
But nine, the set is here is finite because P is finite. So how it is equal to the sigma Borel algebra because
Is-
I didn't
Yeah,
get
yeah.
it.
See, the thing is that this R you can vary, right?
Yes, sir.
So R is in your control. What you can do is, so there are, uncountably many R's in this mod R less than or equal to 1, right?
Yes,
Can
sir.
you not, can you not use that somehow?
Sir, this irrational number are
Yes, yes. These irrational numbers are also dense in R, right?
okay, okay, sir.
Yeah, so given any real number, you can find one irrational number close enough to this. All you have to do is you have to adjust this m by 2 to the power n factor.
Okay, okay, sir. I will. Yes, sir.
So yeah, perhaps you can try. Actually, I have not tried the solution, but yeah, you can try. I will also try. Perhaps
Okay,
next
okay,
time we can discuss this.
okay, sir. One more. I think, sir, in this example number two, I think there is some mistake or in.
I don't know. Actually, assignments I don't make. So
So
okay,
this
you tell me what is. Yes.
in this the image is in minus infinite. It doesn't exist finitely.
Images is what?
The
Ah,
image
yeah.
in
If you take the minimum, then yes, yes. Yeah, that
so
function is not defined.
I
Uh-huh.
think there is some mistake in this notations or
No, but see, it should be maximum, right?
yeah, sir. Then
Correct.
it becomes finite, and then I think
Yes.
the it has meaning.
So, do you remember last time we discussed this function? This is what? This is the greatest integer function. Remember?
Yes, sir. Yes, sir.
Yeah. So consider this to be the maximum of all those. Then now
Ah,
tell me
yes.
what is the answer.
This come to my mind that it either it should be maximum or there's some n greater than equals to x.
Right, right. Yeah, it is it should be the maximum. Now you tell me what is the answer.
So it is monotonically increasing.
Yes. And is it right continuous?
I'm thinking, sir.
Okay.
I think no.
It is not right continuous. Okay. For you, what is the definition of right continuity?
No, sir. It is right continuous. Sorry.
It is right continuous. Okay. Why is it right continuous?
So because the maximum would be the obviously
Yes.
it is either least integer function or greatest integer function.
Yeah. It is. Suppose it is the greatest integer function, but why is it right continuous?
Yeah, sir. Because the greatest integer function obviously it means that the integer less than or equal to the real number.
That is fine. But okay, what do you mean by right continuity? You tell me that first.
So every sequence converging to the real number from right side, the
Uh-huh.
image sequence should be also be convergent to the image of the function.
Correct. Okay. So let us fix a real number x. Okay, then this greatest integer function, let us call it n naught.
I stop it presenting.
Yeah, you stop presenting so that I can start. Okay, can you see my screen?
Yes, sir.
See. So let us look at the greatest integer function. Okay. So fx is what? It is the maximum of all those n such that n is less than or equal to x. Or some we usually write it as this bracket x. But anyway, uh, what we want to do is let us fix one x naught in R and let f of x naught be n naught. It has to be some integer because that is the definition of f of x. And let us take a sequence xn in R such that xn is bigger than x naught and xn converges to x naught from the right, right? So writing this means from the right. Do you agree?
Sir.
Okay. So see, so let us draw something. Somewhere here is n naught plus 1, and somewhere here perhaps it is x naught, right? Yeah, it has to be here, correct?
Yes, sir.
Yes. And then we have a sequence. So that sequence could be anywhere, x1, x2, x3, and then maybe x4 is here. But then after a certain stage, what will happen? It has to come inside this n naught plus 1 to n naught, right? So here will be xn plus 1, and so on. It will come closer and closer to x naught. So there will be certain stage, say m, such that for all n bigger than or equal to m, xn is less than n naught plus 1 and bigger than or equal to x naught. Once this happens, what can you say about fxn? You notice that this is already bigger than or equal to n naught. Okay. Yes. So tell me, what is f of xn? Just by looking at this.
Sir.
Yeah, I could not hear you. Could you repeat?
Sir, N naught.
N naught, right?
Yes, sir.
So after a certain stage, this is a constant sequence. So for all n bigger than or equal to m, fxn is n naught. So what can you
Yes,
say about limit of fxn?
sir, N naught.
N naught, right? Which is f of x, which is f of x naught. Therefore, this f is right continuous.
Yes, sir.
So I hope it is clear. Yes, is it clear?
Yes, sir.
Okay. Any other questions you have?
No, sir.
No.
No,
Nothing from the lectures?
no, sir, not yet.
Okay.
In,
So,
this means it in the assignment it should be maximum.
yeah, it should be
Oh,
either maximum or, yeah, it should be maximum if we are expecting it to be right continuous. It has to
yes,
be
sir.
the maximum. See, for, exercise, just as a thinking exercise, you can think of what about this function. Fx is minimum of all those integers which are bigger than or equal to x. So first of all, you have to argue why does this minimum exist? Why minimum exists? And then you can ask whether f is increasing, decreasing. Or if what about continuity? Right continuous, left continuous.
Yes, sir.
Okay, and so on. So you can ask this. Okay. So, all right. If there are no more questions from your side, what I was doing is I was just recalling what we have done in week four. In week four, we had this problem that suppose we are given a measure on a collection of subsets and we are given a bigger collection, we want to extend this mu to the bigger collection C prime and whether it is possible. So in some cases, we have seen that if we have a semi-algebra, then we can extend the measure to algebra. And how did we do that? Let us recall. So suppose C is a semi-algebra and mu from C to 0 infinity is a measure. Then we can let AC be the algebra generated by C. Then we can define mu tilde on AC as follows. Mu tilde of E is summation I from 1 to n mu of EI, where E can be written as a disjoint union of EIs. For EI in C. And why are we able to write this is because we know that the algebra generated by a semi-algebra has this particular form. All the sets are always of the form disjoint union of
Yes, sir.
EIs as EI varies in C. Okay. So in the lectures, we proved that this mu tilde of empty set is empty, 0 and mu tilde is finitely additive. But this does not tell us this is a measure, right?
Yes, sir.
Can we conclude from here it is a measure?
No, sir, it should be countably additive.
Exactly. So we have to look at whether this mu tilde is countably additive or not. So what do you think? Is it going to be countably additive? Well, we expect it to be, right? Yeah. So to prove that it is countably additive, what should we do? Yes, tell me. To prove that it is countably additive, what should we do?
So to prove it countably subadditive,
No, we have to prove it is countably additive, right?
no, so by this that relation, that theorem, that if set function
Ah,
from
yes,
algebra
yes,
to,
correct. So either we have to prove it is countably subadditive, in which case by that finite additivity it automatically becomes countably
yes,
additive,
yes, sir.
or let us use the definition of countable additivity, right? That we
Yes,
can
sir.
do. So what is the
Okay.
definition of countable additivity?
Just a countable union of mutually disjoint subsets. The measure is equals to the summation of that.
Exactly. So let us start with a disjoint countable union of subsets of AC. So let En be a sequence in AC. So I'm just calling it a sequence because we are enumerating it. Otherwise, I could also write it as a collection En. It doesn't really matter. The sequence in AC and let E be the disjoint union of Ens. Or, okay, maybe I shouldn't write it like this. Be a sequence such that En intersection En, this is empty for n not equal to. And let E be the union of Ens. So now this union is automatically a disjoint union. Okay. What I want to do is, we want to prove that mu tilde of E is summation n equal to 1 to infinity mu tilde of En. Provided, see the issue here is there is no guarantee that this is inside AC. Correct? Do you agree with this?
Yes, sir.
Yeah, because AC is closed under finite unions, but it may not be closed under countable unions. So we have to prove this equality provided E
Yes,
is
sir.
inside AC. Okay. But once E is inside AC, what can we say about E? Does E have a particular form?
Yes, sir.
Yeah.
Just a
So what is the
finite
form?
elements in
Correct.
sigma
So
algebra.
E is a disjoint union of, perhaps KR, R equal to 1 to L, right? For KR in this semi-algebra. Now, uh, okay, once we have this, can I write KR as E intersection KR? Is this true? Oh, I wrote E intersection ER. I meant E intersection KR.
Yes, sir. For every R.
Yes, for every R, right? 1 to L. So, therefore, this KR basically, this can be written as a union of n equal to 1 to infinity EN's intersection with KR. But then this is a union of n equal to 1 to infinity En intersection KR. Is that right?
Yes, sir.
Okay. But what about ENs? ENs are also elements of the algebra. So what does this imply?
So I have a doubt. So
Yes.
we have to prove it is a countably additive. So sir, the sequence we are taking, to we have to suppose we have to assume it should be in the algebra.
Yeah, that's what I'm saying. That the union should be again in algebra. Otherwise, the left hand side won't make sense, right?
Yes, sir.
Uh,
So you have
So
written no guarantee that it should be in the algebra.
no. I'm writing that this union, not always this union is not in algebra, right?
Yes, sir. Yes.
Yeah. So next line I am writing, we have to prove this equality provided E is inside the algebra.
Yes, sir. Yes, sir.
Okay. Now is it clear?
Yes, sir.
Okay. So right. Now let us look at En. En is in the algebra, so it means that En itself can be written as a disjoint union of something. So it is the disjoint union of, say, ENI's I running from 1 to, say, suppose KI, right? For some ENI's in C. And now if I substitute it there, then this KR is going to be union n equal to 1 to infinity, union I equal to 1 to KI. Oh, yeah. So this should be KN. KN ENI intersection KR, right? So I can again use the associativity and all. I can take these two unions out. Yeah. So I hope this is fine. Let me call it equation 1. Similarly, what I can do with En is I can write En as E intersection En. Is that right? Yes. Yeah. So again, but now I will write E as the union of KRs. So it is union R equal to 1 to L KR intersection with En, which is union R equal to 1 to L KR intersection En. Okay. And then just I will write this En also again, R equal to 1 to N, union I equal to 1 to Kn, KR intersection ENI. Okay. So now we have these two sets, but notice that the first set, this is inside C, on the other hand, this is inside AC. Okay. So, right. I know that mu tilde of E this is equal to summation r from 1 to L mu of kr. Is that right?
Yes, sir.
It is right. Next one is, so this, let me write kr as mu of union n equal to 1 to infinity, union I equal to 1 to kn, eni intersection kr. Notice that this is an element of C. So I can use this given mu. And this is a countable union. Countable mutually disjoint union.
Yes, sir.
So I can take the sum outside, and this becomes r from 1 to L, n from 1 to infinity, I from 1 to kn, mu of E and I intersection kr. But then, since these are all non-negative terms, maybe some different color. These are all non-negative terms, so I can interchange the order of summation without causing a problem in the extended real numbers.
Yes.
R from 1 to L, I from 1 to kn, mu of E and I intersection kr. But then again, from here I can write like this. Summation n from 1 to infinity, mu of union r equal to 1 to L, union I equal to 1 to kn, EIN intersection kr. Because again, this is a disjoint union, but now this time it is finite. So I can again, finite unions are countable unions.
Yes, sir.
So this is n equal to 1 to infinity. Now by definition, this is mu tilde of ENs, right?
Yes, sir.
So this directly proves that mu tilde is countably additive and therefore a measure. EC, and hence it is a measure. Okay, is this clear?
Yes, sir.
Ah, okay, fine. So, okay, next thing, there were two exercises given during the lectures. Have you looked at those?
Yes, sir. I have not tried it yet. I have completed the lecture just before the problem solving session.
Okay. So you have seen the lectures, right? There were two exercises. One was about another definition of the outer measure,
Yes, sir.
and the second exercise was about some particular example of a measure, and then some outer measure was given. You have to calculate something.
Yes, sir.
So that I will not do. Let us look at another definition of the outer measure. Okay.
Okay, sir.
But before that, the calculative part, I hope everybody can do. If you're not able to do, you can contact me and then we can discuss. But yeah, so let us look here. Uh, okay. So first, let me ask a question. Suppose that we are given some collection of sets, or say suppose a countable collection of sets. So this is a sequence in Px, and let A be the union of Ans. And this is not necessarily disjoint. Okay. The question is, can we find another sequence Bn such that Bn intersection Bm is empty for n not equal to m, and A can still be written as union of Bn's. So what do you think? Is this possible?
Yes, sir. We have,
Huh?
sir, in algebra, yes, it can be. If it is a algebra, yes, sir, it can be written as.
It can be written? No,
Yes, sir.
just for the timing, assume that we are in the power set of X.
Yes.
Just forget about everything that we have seen. This is basic set theory question. Given some sequence in the power set, we have the union. Can we find a sequence in the power set which is mutually disjoint, but the union is still the same? Yeah. So, what do you think? Is it possible?
One second.
Okay. Why did you say that it is possible in algebra?
Oh, so that A2 is equals to A2 minus A1. Sorry, A3 is equals to A3 minus A2 union A2 union A1.
Uh, so, see that all things can be done in power set also, right? Power set is an algebra.
Yes, sir. Yes, sir. It is possible.
All those things we can do here. Actually, the
Yes.
reason I took power set is because inside power set we can do everything. All possible set operations they are closed when we take power set.
Yes,
So
sir.
the basic idea is what? Suppose we are given this sequence. This is A1. This is A2. This is A3. See, this is A4. Perhaps this big one is A5, and then so on. A6 and then so on. So what I want to do, let us try to write this as a disjoint union. So I have to collect sets such that every time I collect a new set, it is disjoint from the previous ones. So what is the natural way to do it? Let us look at this set.
Yes, sir.
Let us call it B1. Next, let us look at this set. It is the almost same color. Uh, Sorry, I yeah. Now it is fine. What color? Green color is fine. Let us look at this set. Let us call it B2. So the green one is B2. Next, let us look at B3. So I want to do it from A3, but there are these intersections. I will ignore them. I will look at this. I will call this as B3. Next, at B4. So from A4 I want to construct. I will ignore the previous intersections. So this is B4. And then, we can continue this way. So B5 will be somewhere here. So every time I am constructing new set, I am taking care that the new color does not go inside the old color. And then
So
B6
the
somewhere
diagram.
here. Yes. Uh, are you
So
saying something?
yes, sir. It's very understandable from the diagram.
Right, right. So basically what I want to do, let us define B1 is A1 and Bn is An difference union I from 1 to n minus 1 Ai for n bigger than or equal to 2. Okay.
So,
Yeah. Now the first question is this is a sequence of sets whether it is mutually disjoint or not. So question is Bn intersection Bm whether this is empty for n not equal to n. So let us calculate Bn intersection Bm. Uh, this is oh well. Okay, let us just assume that something is bigger. Suppose that n is bigger than m. N is bigger than m. Then Bn it can be written as An difference union I from 1 to n minus 1 Ai, which is the collection of all elements from An such that x is not in Ai for I equal to 1 to n minus 1. And in particular, if x belongs to Bn, then x does not belong to Bn. Okay. Is that fine?
yes, sir.
Yeah. So, there cannot be an element in the intersection basically. So I mean, this implies that Bn intersection Bn, this isn't. Okay. So at least this question is fine. Now the next question is whether the union is still the same. Is union Bn's equal to union An's? So how do you prove that two sets are equal? You have to prove that each of them is a subset of other. Now which way is easy?
So union of ANs
Yes, union of An's.
BNs.
See, the other way is easy, right? Because union of Bn's are subsets of An's. Therefore, union of Bn's must be contained in union of An's. Isn't that
Yes.
true? Bn is contained in An. Therefore, union of Bn is contained in union of An. Okay. So we have to prove that these are equal. Suppose they are not. It means that this union of Bn is strictly contained inside union of An's. Suppose there is some element x in this union, An, such that x is not in this union. But x not being in the union, this is same as saying that x belongs to a n naught for some n naught, but for every n, x does not belong to Bn. Is that right? Yeah. But then, in particular, x does not belong to Bn naught. This implies x, yeah. Oh, but x could have been earlier. Okay, that we'll see. What we'll do is, okay, fine. Here, let n naught be the least n such that x belongs to an. Why does such a least n exist? Due to the well ordering principle. Then x does not belong to Bn naught implies that uh, x does not belong to this an naught difference union I from 1 to n minus 1 ai. But then, this means that either this does not belong to an naught or this belongs to the union, and both of them are contradictions. This I know is not true, and this thing contradicts the least, I mean, the minimality of n naught.
Yes, sir.
Okay. So therefore, such a thing cannot happen. This assumption is wrong, and if this assumption is wrong, then the two sets must be equal. Okay. So every union can be written as a disjoint union. That is what we have proved. So see, in between what all things we have used? We have used complements and finite unions and finite intersections, right? There is nothing else that we have used. Do you
Yes,
agree?
sir.
So therefore, all this construction, it is still true inside an algebra.
Yes, sir. It is an algebra.
This construction is true for any algebra. That means what we have proved is, given a sequence in an algebra, in, in an algebra A, we can find another sequence Bn in A, which is mutually disjoint with Bn intersection Bm is empty for n not equal to m, and the union still remains same.
Yes, sir.
Okay. So now we are going to use this somewhere, and where we are going to use this is to get another definition of the outer measure. So now my claim is mu star e. This can be written as infimum of summation I from 1 to infinity mu ai's, such that E is contained in union of AIs. AI are indeed elements from the algebra, and AI intersection AJ is empty for I not equal to J. Okay. So, all right, let us, for the time being, let us call the right hand side as S. Let S be this infimum. Mu AI is contained in this union. AIs come from the algebra. AI intersection AJ is empty for I not equal to J. Okay. What can you say about mu star E and S? How can we compare them? So we want to prove that they are equal, but at least do I have an estimate which one is bigger and which one is smaller? Yes. Can you guess?
So you have taken mutually disjoint sets in both the definition.
Yes, I know. So the first one is my claim. I have to prove that it is true. So, but mu star E already has its own definition, right? How is mu star E defined? Can you recall? See, mu star E. What is the definition? Can you tell me?
Yes, sir. It
Tell
it
me.
is same, but it is the sets should must not necessarily be mutually disjoint.
Correct. So it is almost the same definition. E should be covered by AIs, and AI come from E. We are not putting the imposition that AI should be mutually disjoint, right? So these are two real numbers, right? This
Original
S is a real
definition
number.
contain the definition we have to prove.
I could not understand. Could you repeat?
So the original definition is a
Uh-huh.
subset of the new definition.
Not exactly, right? See, which one is a subset of which one? So are you saying this holds?
I think yes,
See,
sir.
no. See, subset means what? You take any element here, it should be here, right? But that is not true. In fact, the other way is true. You take any covering which is mutually disjoint, it is already a covering, right? So this must be true.
Okay.
Yeah, is it clear? Yes, Prasantip, is it clear?
Yes, sir. Because the the mutually disjoint. Yes, sir. It is a smaller set. So, sir, its infimum is bigger.
Right. So what I can say is that mu star E is less than or equal to S. That is clear, right? This much is fine, but I have to prove they are equal. So what is the next thing I have to do?
So, to let an element in S and to prove it in the original
Yeah.
definition.
No. See, S is a real number. S is not a set. I have to prove that
Okay.
S is bigger than or equal to mu star E.
Okay.
It is enough to prove S is less than or equal to mu star E. But how will I prove that? Uh, by saying that every element inside this set, every element inside this set is again inside this set. Once I prove this, then they are same. So let us start with the covering of E. Let AI be a sequence in the algebra such that E is covered by AIs. So this is not necessarily disjoint. That is the main point. Not necessarily disjoint. But somehow we want to construct a disjoint covering of E. So how do I do that? Can we do that first of all?
So from this covering, we have to construct a disjoint covering.
Yes, yes. We have to construct a pairwise disjoint covering. Is that
Yes,
possible?
sir. By the earlier result,
Exactly. So we have seen that in an algebra, given a countable union, I can make it pairwise disjoint without without really changing the union, right?
yes, sir.
So there exists another sequence such that E is contained in this union Bi. In fact, this union Bi is equal to union Ai, and Bi intersection Bj is empty for I not equal to 3. Okay. So okay, now the thing is, can I say that S is less than or equal to summation I from 1 to infinity mu Bi? Can I say this? Yes.
So S is any single element, you know.
No, no. S is this infimum. That's what I'm saying. S is not. S is a real number. S is the infimum of some set.
Yes, sir.
Yeah. Why? Why is S less than or equal to this sum? You said yes, so you should also know why, right?
Um, yes, sir. It also belongs to S. That
S
is,
is not S is not a set. That's what I'm telling you. S is the infimum of a set. Do you want to say that this belongs to this set? Hello. Yes, are you here?
yes, sir.
Yeah, yeah.
And
So do you want to say that this countable sum belongs to this set? Is that what you mean? Okay, what do you think? Yes or no? Simple.
yes, repeat the definition of S to me.
See, S is the infimum of this particular set. I've written the definition, right? Can you see this?
Yes, sir.
This thing here?
Yes, sir.
This is the definition of S. So S is a real number because it is the infimum of some set or perhaps an extended real number. You cannot say that something belongs to S. You can say that something belongs to some set. Now, which set do you want to say? Tell me.
Okay. Okay. Okay.
No, that is fine. But you, this countable sum, does it belong to this set? Okay, let me write it if it is confusing for you. I am asking whether I from 1 to infinity mu bi, this belongs to I from 1 to infinity mu ai, such that E is contained in union ai intersection aj is empty for I not equal to j. And indeed ai should come from this algebra. Yeah. So I'm asking you this, whether
Sir,
this is
yes,
true.
it should
Yes,
belong.
right? Because BIs, that's how we constructed. They are mutually disjoint and they still cover E. So
Yes,
this
sir.
is true.
So, sir, it is true then. S is
Right.
less than. Yes, sir, it is
So
true.
this is an element of this set. S is the infimum and therefore a lower bound. So this
Yes,
must
sir.
be true.
Yes, sir.
Okay. But can we also say that summation mu bi, this is further less than or equal to summation mu ai? Can I say this? Yes.
So, in right hand side, it is AIs are some particular.
Yes. AI is a particular what?
So, it is a set or
Yeah, it is a set. Right? So do you remember how these AIs were? So AIs were anything which cover E. The union of AIs cover E. That is all we have with us.
yes, sir, it is true. It should be
Why?
equal.
It should be equal.
No, no, sir,
Why?
no,
Why? Why?
no.
See, it is not equal, right? Why is it not equal? That counter example is very simple. Just look at these two intervals. Say suppose 0, 1 and half to 3 by 2. Then this summation of this, basically the length of 0, 1 plus length of half 3 by 2. This is equal to 2. But now if I want to write it like this, then it becomes what? 0, 1 plus length of 1 comma 3 by 2, which is not 2, which is just 1 plus half, which is 1 and a half, right? So in general, they are not equal. But at
Yes, sir.
least, yeah, is can I say that is less than or equal to?
Yes, sir, because BNs contain in ANs.
Exactly. So why is this true? Is because Bn is contained in An and mu is a measure, so mu of Bn must be less than or equal to mu of An. This
Yes,
implies that this sum, mu Bn, is less than or equal to this sum. Again, notice that we can do all this only because each of these term is non-negative. If we
yes,
had some different
yes,
types of real numbers, we cannot really compare them. So all
okay.
these things happen because the measure is non-negative and all. So this is true. So what I have is S is less than or equal to this mu of AI. So from here, can I say that S is a lower bound for this set. Summation I from 1 to infinity mu ai, where E is contained in union ai, and ai just come from E. Can I say this?
Yes, sir.
Now, S is a lower bound, mu star E is the greatest lower bound, and therefore S must be less than or equal to mu star E, right?
Yes, sir.
So we started with mu star E less than or equal to S. We also proved that S is less than or equal to mu star E. Therefore, mu star E must be exactly equal to S. And what was S? By definition, it was infimum of summation I from 1 to infinity mu ai, where E is contained in ai intersection aj is empty for I not equal to j. Okay, so is this clear?
Yes.
Okay. So, all right. So that second exercise you try.
Okay,
Maybe in
sir.
the assignment questions also it might have something from that exercise. And if you're not
Okay.
able to do it, we'll discuss it next time. So,
Okay.
are there any questions? Any more
So
questions?
that problem number 9, I I will try again and then we
Yes, yes.
discuss. Yes, sir.
Yeah. In between, you can contact me by mail if you want to. And yeah, another thing is somebody had asked about right continuity, but I don't think they joined today. So let me just give the definition. And we have already seen that greatest
Thank-
integer function is right continuous.
Yes, sir.
So okay, so of course this will be
Thank you.
uploaded later to YouTube and all. So
Yes,
just
sir.
we'll end, but after writing a definition. So let f from R to R be a function, then f is right continuous, and similarly one can define left continuous if for every sequence xn in R with the property xn bigger than or equal to x naught for every n, and xn converges to x naught, we have sorry, right continuous at x naught, I mean, at x naught in R. If this happens, we have f of x naught is equal to limit of f of xn. And equivalently, what I can say that in this neighborhood we can do the things. For every epsilon positive, we can find a delta positive, such that for every x in x naught comma x naught plus delta, we have mod of fx minus fx naught is less than epsilon. So yeah, so maybe I'll leave this as an exercise that these two definitions are indeed equivalent. Check if these statements are indeed equivalent. And just one more remark is that this right continuity and left continuity we can define only in R, because there only in R we have a greater than equal to relation. Or other species such as R2, R3 or general Rn, we cannot do this.
Yes.
We require some different type of things there. Okay, so if there are no more questions, then we can stop.
Okay, sir. Thank you.
Okay, bye.